Hi there, class. This is Mrs. Brunk. Thanks for joining me for lesson 6-4, factoring polynomials. In this lesson, we will answer the essential question, what are some ways to factor a polynomial and how is factoring useful? Well, we've already done quite a bit of factoring in this course, and so a lot of what you'll see today will seem like review, but we will introduce a few new factoring patterns. So you probably already can reflect on how it's useful. We looked at factoring as a method to solve quadratics, among other methods. And so we're going to look at see how that there are other, and we also looked at factoring to find out, say, for instance, when a quadratic parabola would cross the x-axis, or if it would even cross the x-axis at all, if it was not factorable, or if it was some that are not factorable cross too. But so anyway, we really pretty much studied factoring in conjunction with quadratics. But now that we're studying higher degree polynomial functions, we are going to be relying on factoring to tell us some things about polynomials. So we also did some factoring called grouping, and we looked at some special patterns of the difference of squares and perfect square trinomials. So we'll review those, and we'll learn a couple new factoring methods. So factoring out the greatest common monomial first. So that's our, remember when we filled out our factoring flow chart, we put that right at the top. Take out a GCF, and that kind of ends up either revealing some special patterns or something easier to factor. So that's always what we look for first. So most polynomials cannot be factored over the integers, which means to find factors that use only integer coefficients. But when a polynomial can be factored, each factor has a degree less than the polynomial's degree. So for instance, when we factored quadratics, we got our factors were, the variable was to the first power, right? They were linear factors. So while the goal is to write the polynomial as a product of linear factors, that is not always possible. When a factor of degree 2 or greater cannot be factored further, it is called irreducible factor, or an irreducible factor. Sometimes people will just say it's not factorable. But sometimes they'll use the term irreducible factor so that maybe you've done some factoring, but then you get down to a point where you have a degree 2 or higher and you can't break it down any further. So then you might say that that particular factor is irreducible, can't be reduced anymore. So let's take a look at the first polynomial we're going to factor. Now, if you look at that polynomial, the first thing I see is there is a GCF. So that's the first thing I'm going to do I am going to take out that GCF, which I can see is 3x. So when I take that out, what's left over that first term is 2x squared, and what's left of the middle term is 5x, and then finally what's left of that final term is 2x, or sorry, just 2. And if I was just looking to find a GCF, then that would be done. That would be, I've taken it out. But because our goal is to factor these, we want to see if we can go any further. And with something like this, remember when we start a quadratic trinomial with something other than just x squared, we want to use the AC method. So the AC, when I multiply the a and the c, I get 4. 2 times 2 is 4. So I'm looking for factors of 4 that will make add up to the middle term, which is 5, and that's 4 and 1. And so now what I can do is take and split that, rewrite that trinomial as 2x squared, and I split the middle term. And you can either write 4x first or 1x first. I'm going to write the 4x first and then the plus 1x. So I've essentially just split that middle term now into two separate terms that do add to 5x, but just now we have two terms. And then plus 2, and then I can rely on my factor by grouping, right? So I have to, of course, continue to bring that 3x down. So then when I split the 4-term polynomial up, I'm looking for the GCF. I'm just going to bring that 3x down and put it as part of my final answer, and then just focus on breaking down the factor by grouping. So I can see out of the 2x squared plus 4x, I have a 2x I can take out. And when I do that, what's left over is x plus 2. And then out of the second pair, there's really nothing, but I have to be able to take something out. So when I can't take anything out, I take 1. So I'll pull out a factor of 1, which leaves me with x plus 2. And then you see that common binomial factor of x plus 2, which means that the coefficients, or the GCFs that I took out front, the 2x and the 1, create one of my binomials, and the x plus 2 is the other. So for a final answer of 3x times 2x plus 1 times x plus 2. So distributing that back out gives us a cubic polynomial, so it gives us a degree 3 polynomial. So now we're going to be looking at these polynomials that are higher degree and breaking them down using methods that we learned earlier with quadratics. So let's take a look at the next one. So in the next example, I see that there's a GCF of 2x. So I'm going to take that out, and what's left is an x squared out of the first term, and then minus 10. Now I always want to see when there's a degree on a polynomial, like in this case of 2 or higher, I want to see if I can break that down further. Now we learned a special factoring pattern with 2 terms called the difference of squares, but in order for me to use that here, I would have to have a difference, which I do have, and I have to have 2 perfect squares. Well, x squared is a perfect square, but clearly 10 is not, and so I can't do anything more with that. That part is irreducible, the x squared minus 10, and so I know that my final factored form is just that 2x times x squared minus 10. So let's move on and take a look at the next few questions. Now these first 2 questions in the reflect portion refer back to that x squared minus 10 factor that we had there. And why wasn't the factor x squared minus 10 further factored? Well, we just mentioned that was because that 10 is not a perfect square. And so there's no way with integers, which is how we typically, we think about factoring, there's no way to break that down because the square root of 10 is not an integer. So yeah, and the reason why is we can't use the difference of squares pattern. So it's basically what we just answered. Now then it says, consider what happens when you factor x squared minus 10 over real numbers and not merely integers. So now if we say, well, we just have to make sure they're real numbers, they don't have to necessarily be integers. So that would include things like decimals, fractions, square roots that are irrational, things like that. So if you think about that difference of squares pattern, what we typically do is we write 2 binomials, one that's a plus and one that's a minus. They both start off with the square root of the first term, so we could do that here. They square root x squared, I get x. Then I'm going to have one factor that's a plus and one that's a minus, and that's why we don't have a middle term when it gets expanded back out. And then typically what we do is we take that last term and square root it, and then we put the square roots there as your other parts of those binomials. But because I can't technically square root 10 and get an integer, I'm going to just instead write it as the square root of 10 for my other factor. So you can see how that would come in handy if, say, we were trying to solve that quadratic. We could now see that we have two binomial factors that we could set equal to 0. Let's try one more. Actually, this one is going to be a U-turn question, your turn, excuse me. And so I want to have you pause the video and give this one a try. Try to factor it as far as you can go. So keeping in mind that you may have to use the either easy or AC method to factor once you take the GCF out. So pause the video now and give this one a try. All right, so thank you for giving that one a try. And that one, once you took the GCF of x out, you were able to use the AC method. Hopefully you're able to remember that. It came back to you. I remember we did quite a lot of practice on that with like Who Killed Mr. Factor, and there was another one I can't remember. We did a lot of AC factoring on, so hopefully that came back to you quick. And so our final answer is x times 3x plus 4 times x plus 1. And remember that the order of those terms is not important. You could have had the x plus 1 term first and then the 3x plus 4 term. And I guess technically even you could have had the x in any of those positions, but usually if you have a monomial, you put that out front. So, all right, let's move on and take a look at the next question. So we just mentioned the difference of two perfect squares pattern, and remember that occurs whenever you have two perfect square terms and then a subtraction sign. So if you have a difference of two squares. And the factoring pattern for the difference of two squares, you have two binomials that have different signs. One's a plus and one's a minus. And the terms within them are just simply the square roots of the first term and the square roots of the last term. And so because they are nearly identical, the only thing that's different is the sign. When you go to FOIL them back out, the middle term would turn out to be 0, and that's why you just see two terms instead of three. Now, perfect square trinomials, we've done quite a bit of work with perfect square trinomials. Remember that perfect square trinomials start with a perfect square, they end with a perfect square, and the middle term is twice the product of the square roots of those two terms, the first and the last. And it doesn't matter whether the middle term is a positive middle term or a negative middle term. It still would create a perfect square trinomial were that pattern to hold. And the only difference would be how when you factor it. So if you have something that kind of follows that pattern, you'll end up with two identical binomials that you can instead write, instead of two separate binomials, you can write it as that binomial squared. So, for instance, if you had a squared plus 2ab plus b squared, when you factor it, you'd get an a plus b and an a plus b, which would be an a plus b squared. And then alternatively, if the middle term is subtraction, you'd get an a minus b squared. Well, today we're going to focus on two new patterns. They are called the sum and difference of cubes. Now notice there's a sum of two cubes and there's a difference of two cubes. But when we looked at the pattern with squares, it was a difference of two squares. Remember, there was no such thing as a sum of two squares because if that last term was positive, which would be the case if that was a sum of two squares, then you'd have to have two binomials with the same signs, and therefore then the middle term would not cancel out. So, but when it comes to cubes, there's a special pattern for a sum of two cubes and a difference of two cubes. So we're going to take a look at how those work, but this is the special pattern that a cubed plus b cubed is equal to, and notice the factored form has a binomial and a trinomial. The binomial is a plus b, which, as you can see, means it's the cube root of the original terms. It's the cube root of the a cubed, which is a, and the cube root of the b cubed, which is b. And then the trinomial actually ends up being kind of following this pattern. The first term is the square of the first term of the binomial. So that was an a, so if I square, that's a squared. The middle term is the product of those two terms, a and b, which would be ab. And the final term is the square of the last term. And then the signs, there's two different patterns depending on whether this is a sum of cubes or a difference of cubes. If it's a sum of cubes, it starts with a plus and then alternates. So it's plus minus plus. Whereas if you look at the next one down, it looks almost identical. But because that one's a difference of cubes, instead the signs work like this. They start off with a minus and then they go plus plus. I'm going to show you a video and talk a little bit about a special way that I call SOAP well, I didn't call it SOAP, but the particular video I found did. The SOAP method that will help you to remember how those signs work, right? So let's take a look at an example. Actually, I'm going to do an example of each, a sum and a difference. So perfect cubes, really good idea to get handle on. I know you probably got a pretty good repertoire of perfect squares, but to have perfect cubes, that's a good thing to have. So like, 1 cube, 2 cube, 3 cube, and so on. So your first perfect cubes are 1 and then 8. 27 is 3 cubed. If you cubed 4, that's 64. 5 cubed is 125. 6 cubed is 216. 7 cubed is 343, and so on. So if you have a nice little list of perfect cubes that you can kind of rely on, then you will come back to when you'll kind of recognize when you see them. So I chose to do x cubed plus 8. And by the way, variables that have exponents will be perfect cubes if the exponent is divisible by 3. So x cubed or x to the 6th, x to the 9th, x to the 12th, any of those would be perfect cubes. So if I wanted to factor x cubed plus 8, the first thing I would do is I know it's a sum of two perfect cubes. Both are perfect cubes, x cubed and 8. So I'm just going to go ahead and set up the format. There's a binomial, and I guess we're going to also do one with a minus 8. So we'll do both. But we're going to set up, and we're going to have a binomial and a trinomial, okay? Now it turns out that the trinomial that you end up getting is not factorable. So that's kind of the nice thing about this pattern is once you find the binomial and the trinomial, you're done. You don't have to dig any further and see if there's more you can do to break down the trinomial. It will be irreducible when you get to this point. It's just kind of how it works. So to get this first binomial, I'm going to take and I'm going to cube root. Well, actually, first of all, I want to review that what we saw like in the video, like what SOAP means. So as far as the signs go, once I get these terms, which we'll talk about how to get the terms here again, but then how I figure out the signs, I fill in the signs last, and that's SOAP, which means it means same. That means the binomial will have the same sign as the original problem. And then O stands for opposite. So the next sign will be the opposite sign of whatever you started with. So if you started with a plus, the next one will be minus. If you started with a minus, the next one will be plus. And then the AP goes together, and it actually means always positive or always plus. So that last sign will always be a plus. So looking at the x cubed plus 8, if I cube rooted x cubed, I get x. And if I cube rooted 8, I get 2. So my binomial is x plus 2. So now to get my trinomial, I look at that new binomial, x plus 2, and I'm going to take that first term and square it. So if I take x and square it, I get x squared, right? Of course. And the middle term, I take and multiply those two terms, the x and the 2, so that'll give me 2x. And then finally, to get the last term, I square the 2. So I square the first term, multiply the two terms, and square the last term, and that gives me these three terms. And then I can fill in using SOAP. I already have the first sign because it's the same as the original. Then opposite of the original would make that minus, and then the final one is plus. So that's where the SOAP comes in. So let's try the next one, x cubed minus 8. So the only thing that's going to change here are the signs, because when we cube root x cubed and we cube root 8, so first of all, we're going to still get a binomial and a trinomial. And when I cube root the x cubed and the 8, I'm still going to get x and 2. But when I get that trinomial, I'm still going to take the x and square it, which gives me x squared. I'm going to multiply the 2 and the x gives me 2x. I'm going to square the 2, which gives me 4. And then the signs are same as the original, which I already put in was the minus. And then opposite of that, so the opposite of a minus would be a plus. And then, of course, the final one is always plus. So essentially, once you recognize that you have perfect cubes and they're either some or a difference, this is kind of how the pattern works. You take the cube root of the two terms to find your binomial. You take that binomial and you square the first term to get the first term. So again, take the first term and square it to get the first term of the trinomial. You multiply the two terms to get the middle term, and then you square, hold on, the last term to get the final term there. And then you fill in using SOAP, which is always a good idea to use SOAP, right? Okay, so we're going to build on that and try some more complicated ones. So the first polynomial I have is 27x cubed plus 64. Well, I recognize right away all those terms are perfect cubes. 27's 3 cubed. x cubed is, of course, x to the third power. And 64 is 4 to the third power. So those are my perfect cubes. So I know I'm going to have one of these special factor patterns. And so I'm going to go ahead and just set up the format. I know I'm going to have a binomial and a trinomial. So to get the binomial, remember I'm going to cube root the first term to get the first term. So I cube root 27, I get 3. I cube root x cubed, I get x. Then I'm going to cube root the 64. So that's 4. So fill that in. Remember, I'm going to come back and worry about the signs later. Now in the trinomial, I take that term, that 3x term, that first term, and I'm going to square it, which is going to give me 9x squared. Then to get the middle term, I'm going to multiply those two terms. So 3x times 4 is 12x. And then to get the last term, I'm going to take that last term and square it. So I'm going to take the 4 and square it. I get 16. And then I'm going to fill in the signs using SOAP. So same as the original, which means that's going to be a plus to start, right? Because the original was a sum. It's 27x cubed plus 64, so it's going to start as a plus. The next sign will be the opposite, so that'll be a minus. And then, of course, the last one is always plus. So that last will always be a plus. That's my factored form. Let's try another one. So we have 8x cubed minus 27. So I got all perfect cubes. So I'm going to set up my format, my binomial, my trinomial. To get the binomial, I'm going to cube root the 8x cubed and the 27, which gives me 2x and 3. And then I'm going to take that 2x and I'm going to square it to get 4x squared. I'm going to multiply the 2x and the 3 to get 6x. And I'm going to square the last term to get that last term. And now I'm going to fill in the signs using SOAP. Same as the original. The original was a difference, so I put a difference here, or minus. Next one will be the opposite of that, which is plus. And then, of course, the last one's always positive. So that gives me my final factored form of that. And in the question number 5, the reflect question, they're referring to this last one we just solved. And it says the equation x cubed minus 27 equals 0 has 3 roots. We're going to see why that is, how we know that later on. But for now, we know that that a cubic function could have 3 separate roots, or it could have one root that counts 3 times, or one root that counts twice, and one that counts once. And we kind of looked at that when we were looking at the polynomial graphs in the last module. So the question is, how many of them are real? Well, remember when we solved quadratics, when we factored, what we would do is then take those factors and set them equal to 0. So let's say I did that here. If I set this 2x minus 3 equal to 0, I could solve that one easily. And then if I set the other factor, which is 4x squared plus 6x plus 9, which again I said is not further factorable. We can't do anything more about that. You could try it if you want to, but you find out it'll never factor in this pattern. So if I set that equal to 0, well, how would I solve that anyway? Because it's not factorable. So think about the other methods we use for quadratics. We used completing the square, and we also used the quadratic formula. So that's something we'd have to do here. Now we could solve that first part, that 2x minus 3. Now they didn't really ask us to solve it, but we'd go ahead and real quick just do it. If I set that equal to 0, I know that I could just add the 3 to both sides and then divide by 2, and that would give me a solution of x equals 3/2. So that's actually a real number. And so I know at least one of the roots is real. Now to take from the other solution, I'd have to actually use the quadratic formula. So remember that's x equals opposite of b plus or minus square root b squared minus 4ac all over 2a. Maybe you're singing the song in your head. That's what I'm doing. So if I wanted to solve the whole thing, I would just plug the a, the b, and the c in, and I would actually solve it. But this didn't ask you to solve it. So here they just want to know, would the roots be real or not? And remember, there's this thing called the discriminant. That's the b squared minus 4ac part. And if we just plug the b squared and the b and the a and the c into the discriminant there, it'll just tell us by the value of it whether we're going to get real solutions or not. So if I substitute my numbers in, well, the b is 6, so squared, that's 36, minus 4 times the a is 4, so 4 times 4, and then the c is 9. And put that on my calculator, I got negative 108. Well, remember what we're going to do with that right now is if we were to go to solve this, we'd end up having to take the square root of a negative number. So we know right away that means that there must be two non-real roots that come from this part of that polynomial. We'd end up getting answers that had I in them, right? So there's one real root, that's that 3/2 that we found here, and then there would be two non-real. And we could continue on and actually go through and finish and solve this, but that's for another lesson. Right now, we just want to know what kind of roots would there be. So if we can get it down to a quadratic, we can always test the discriminant. Okay? Well, that leaves us one you try question here. So I'm going to go ahead and pause the video and give you a few minutes to give this a try, and then be sure to tune back in to test your, and I guess probably should tell you, maybe I'll get you started on this you try question. You're going to want to take out a GCF of 5x first. So first do that, because right now you can see, that doesn't look like it's a sum or difference of cubes. But if you take out the 5x, it ends up with this. So then you can go from here, finish it up. So pause the video now, finish this up, tune back in to check your answer. Okay, so thanks for giving that a try, and this would be your final factored form. So again, the binomial is the cube root of 8x cubed and 1, so that's 2x and 1. Take the 2x and square it, you get 4x squared. Multiply the 2x and the 1, you get 2x, and square the 1 and you get 1. And then fill in your signs using SOAP. Okay, now it comes to our last practice at factoring. And that brings us to factor by grouping. So this is something that we've worked with, and we've definitely worked with it as we were doing the AC method, because you remember how you turn a trinomial into a 4-term polynomial by using the AC method. And that's exactly when you want to use factor by grouping. Anytime you have an even number of terms beyond 3, so if you have 4 or 6 or 8, we haven't gotten that elaborate yet to where we've done any with 6 or 8 yet, but we'll certainly start throwing some of those in. Right now we're looking at, we have 4 terms. So when you have 4 terms and you want to factor that, the easiest thing to do is to first of all make sure it's in descending order of powers, and then split the 4 terms up into 2 groups of 2. So like for instance with this first one, x cubed minus x squared plus x minus 1, if we split those down the middle, then we could focus on the first 2 and find the GCF. Well, the GCF of x cubed and x squared is x squared. So I could take an x squared out of both of those, leaving me with x and a minus 1. And then looking at that second pair, x and minus 1, there's no common factor. But you know, you can always take 1 out of anything. So if I take a 1 out, that would leave me with x minus 1. And now I have that common factor, right? That x minus 1. So then creating that factored form, we have the 2 GCFs that we took out become one binomial together. So that's x squared plus 1. And then the other factor is x minus 1. Now again, notice we have a sum of 2 perfect squares. So that's not factorable. Now if that had been an x squared minus 1, we could have broken that down further. And so you always want to be on the lookout for that, but that x squared plus 1 is irreducible. You can't go any further with that. Now looking at the next one, split down the middle, I'm going to take out an x cubed out of the first pair, and that's going to leave me with an x plus 1. And out of the second pair, I can't take anything, so I'm going to take that 1 out, and that leaves me with an x plus 1. So there's my common binomial. So when I list that out in factored form, that would be an x cubed plus 1 and an x plus 1. But the x cubed plus 1 is reducible because that is a sum of two perfect cubes. So I'm going to go ahead and set up that format and factor and break that down further. That's going to have a binomial and a trinomial. And of course then I still have that x plus 1 factor to contend with there. So when I break down the x cubed plus 1, my binomial is going to be an x plus 1 because I cube rooted both of them, right? And then take the x in squared, I get x squared. Multiply the x and the 1, I get x. Square the 1, I get 1. And then fill in the signs using SOAP. That would be a plus, minus, and a plus. Now notice we have an x plus 1 and another x plus 1. So technically we have x plus 1 squared and an x squared minus x plus 1. So you could also write it in this way in a little more condensed form. Okay, so I want you to give this final one a try, and this will end our part 1 of lesson 6-4. So go ahead and pause the video, give this one a try, and then we'll wrap up this part of the lesson. Okay, so I hope that wasn't too tricky because that one was not factorable. It was irreducible. So, although you could find a GCF out of the first pair, when you got to the second one, you could have taken out a GCF of 1, but that wouldn't help. Your binomials then wouldn't match, and so that's not factorable. So that's going to do it for the first part of the lesson. We're going to leave those applications to talk about on day 2. So here's the end of part 1 of 6-4. Thanks for coming to class.